All right. So here's what we said. So for if I go back and look at this, now apply everything I just said about the mutual fluxes. If I apply that here, all right. Here's what I have for coil A in this setup, where this is 90 degrees, this is 270 degrees. And I call this the AS axis. So A, basically for A on the stator, all right, I'm saying that guy's field is centered around 0 degrees, right? That's where it's got its sort of positive center, where if I think of this guy as being a coil, right? So I think of coil A as just being a flat coil or whatever, right? His field spatially is pointing in this direction, and it's centered at 0 degrees. And so I say that there's this AS axis. All right, now what I want to do is say, all right, I want to understand the mutual coupling between coil A and coil F. So what I'm going to do is, so what I've shown here is I've said that the angle theta R is this angle between the F axis and the A axis. The thing is that the rotor can move as a function of time. It's movable. All right. So if I look at coil F is effectively identical, except that it may potentially have a different number of turns. So if I look at what's happening here, all right, what I'm showing is as I go around from 0 degrees to 360 degrees. So here's 360 degrees. We already talked about what coil A's field would look like. This is 90 degrees here. This is 270 here. If theta R is equal to 0, meaning that those two coils are aligned with each other, then their fields would look identical. And that's what you see in the picture here. Their fields basically line up with each other. So again, just like I did before, I can say the flux from in F from A, if I want to think of it that way, would essentially be some constant value times whatever the A phase current is, times the cosine of the angle between them. So at this particular angle, at theta R, the B field passing through the B field passing between the coils is at its maximum. If I move to theta R equal to 90 degrees, the difference between this picture and this picture is that the coil on the rotor, because the rotor itself basically turned 90 degrees. So when the rotor turns 90 degrees, the two fields are no longer aligned with each other. And here's the picture that I draw. For coil F, it looks like this. Coil A, it looks like this. If I look at how much flux is passing through A from F, what would it be? With their fields off by 90 degrees like this, how much field from F is going through A in total at this alignment? What's the total that would be happening in this particular case? When they're 90 degrees off from each other?
0.
0, right. So, and if I look at it here, now the fields, when I've turned 180 degrees, so again, I let it rotate more. Now the angle between the two axes is, and see the F axis is moving because basically theta R is moving, all right? In this particular case, where theta R is 180 degrees, their fluxes are the same magnitude, but 180 degrees off from each other. And then here, at 270 degrees, where it keeps rotating, right? What I see is that at this particular point, it's again, the net flux is equal to 0. So in general, what I say is that the flux from A to F, and it would be the same from F to A, basically is some constant value times the cosine of theta R times whatever the current is. And if I said, what's it from F to A, it would be the same thing. It would be symmetrical. All right. All right. It would be like that. Now the question becomes in, what happens if I have P poles? All right. So in this particular case, what I'm showing is a machine with P poles. So what's going on in the machine with P poles? Well, what I see is that coil A goes here. Its return side is here. That guy would be connected in series with a second winding. All right. So real quick, I want to understand this picture here for a second, right? Because there's this question I ask you in the homework about the electrical angle and the angle of the actual physical angle around the rotor. All right. So in this particular case, let's assume I only put a current into coil A. All right. And what I see is that coil A is sitting at 90 degrees, and then he's got another side over here at 180 degrees, and then another side here at 270, and another side at 0. Right. Basically, I walked around that guy, but I walk around. This is a 90-degree turn. This is a 90-degree turn. That's a 90-degree turn. That's a 90-degree turn. All right. So if I look at what's going on here, all right, I'm going to say is that coil A is located here. All right. This is where I have the dot. This is 90 degrees. And then over here at, this would be my 180. Okay. And then I have, let's see, there's also an X right there at 0 degrees. And there's another dot over at 270 degrees. Okay, like that. That's the way this guy is set up. So if I go through the way this thing would be set up, just like we did before, I'm going to see my fields for A coil would go into the rotor there, out of the rotor there, into the rotor here, and then out of the rotor here. That's the way we basically think about it. All right. So if that's the case, what I would do is I would say that it goes like this. The B field would alternate like that. So here's 360 degrees over here. Okay. What I'm seeing in this particular case, all right, is the fact that as I go around physically one time, so as theta goes from 0 degrees to 90 degrees to 180 to 270, what happens is I go through 2 periods, right? You can see I went through 2 periods of the field. So what we do is we say that by the time we get through one complete period, we've actually gone through 2 periods. So one period of physically, we've gone through 2 periods of the field. So what I say here is theta electrically, when physically I've moved 180 degrees, electrically I've moved 360 degrees. So I say that the angle electrically is the number of poles, all right, divided by 2 times whatever the angle is that I've gone around physically. Okay, that's the relationship that we have. All right, and that is basically because with the number of poles, you're causing the field to vary twice as fast as you go around this thing. So if I talked about what would the flux or what would the mutual inductance be? All right, the mutual inductance in this particular case, like LAF, right, or let me say lambda AF, that would end up being M cosine P over 2 theta R times IF, right? What we're saying is that if I look physically, so this is theta right here, right? As theta varies around this thing, right? The flux coupling varies twice as fast because of the fact that the fields are moving twice as fast. All right. So in the homework there, I think I ask you to think about the way I say it is you have some number times theta R. You have to figure out what that is based on the number of poles. In this particular case, P is equal to 4. This is a 4-pole machine, so it basically has twice the frequency as I go around. All right, that's the basic concept. All right, now the other part that we need to be able to think through to be able to deal with a problem like that, or really the problem that I have more generally when I'm dealing with these synchronous machines is how do I actually compute the torque, right? So if you go back and you look at the notes and you look at what we discussed previously, what we did was we first figured out what the energy stored in the magnetic field was. The way we did this is we viewed this thing as basically like a transformer with a mechanical port and an electrical port. And I basically said, okay, the rate at which I put energy electrically into the machine has to be equal to the rate at which energy is stored in the field and the rate at which energy is output from the machine. So the rate at which energy is output from the machine is the power, the mechanical power, and the rate at which it's put into the machine is the electrical power. And then we said the rate of change of stored energy is how we compute the rate at which energy is stored in the magnetic field. Now, if this thing can move, mechanical power is torque times the speed, which we write as the rate of change of angle. All right. If it was a linear thing, we'd say force times velocity, or force times dx by dt. For the electrical side, the rate of the electrical power would be V times I. And by Faraday's law, we know that V always has to be d lambda by dt. All right. So if I've got two coils like I do here, this thing, the electrical power has two terms. All right. And so I can ultimately put all of this together and get that the electrical, this is P electrical, and this here is P mechanical. All right. Now, the thing that we worked through is how we calculated the energy. And essentially what I do is I multiply both sides by dt and get that expression, which is a nasty looking kind of integral. And what we did is we said, calculate the energy. It's equal to this IA d lambda A plus IF d lambda F minus tau d theta R. And I have to compute that integral, which is, again, you can go back and look in the notes to see more about this. I'm going to kind of skip through the details, but basically what I got to do is I got to integrate both sides of this expression here, which is this. So you're integrating this guy, which is a really complex path integral. You can go back into calculus and you've seen that kind of thing before. All right, but basically, what I said is effectively computing the energy is fairly simple. I don't really need to know exactly what the path is. I can do this in multiple steps. All right, essentially what I have is these three steps here, and I'm not going to go through the details so that you can read it, right? But there's basically three steps. There's three variables that I worry about, and there's a step for each variable. All right, and I'm doing this specifically for a two-coil machine, right? So if I look at this machine here, it has two coils. If I had 4 coils, there would be 5 steps, okay? So for this particular thing, what I'm saying is I go in basically 3 steps. I assume that there's no flux in coil F and no flux in coil A. In other words, I'm not putting any current in. And somehow I say to myself, how much of a change in energy could there be? Well, the change in energy would be nothing because there's no flux. So this first step, we never even do it basically because we integrate with respect to theta R, but it doesn't change anything. So really, for everything I do, I focus on step 2 and step 3. In step 2, what I do is I basically assume that lambda F is 0. In other words, there's no current going into the F coil, but there is a current going into the A coil. So I compute this integral only doing this term. And then the last step, I basically say, well, I already put in coil A and coil A's current in step 2. So now what I do is I do this integral, all right? And I assume that coil A is already acting. So the way to do this, so step 1, there's nothing to do. This guy is equal to 0. We don't have to worry about it, all right? For step 2, I basically have to compute I d lambda A. Which, if I go through the math here, works out to be 1/2 LAIA. The important thing here is lambda A in general is LAIA plus whatever the mutual is between A and F. But what we're saying is in this particular step, this guy is equal to 0 because we haven't put that in yet. In step 3, now they're both acting. All right, both currents are acting. So I have whatever energy I had previously, and now I have to do it for coil F. But the trick here is that lambda F has LF IF plus it has whatever is coming from coil A. So what I'd have to do is I'd have to solve this expression for IF, plug that into here, and it becomes kind of a messy bit of work to do that. It's not too bad with only 2 coils, but it becomes an absolute nightmare if we try to do this with 4, right? So how can I get around this, right? So the energy in general, all right, the energy, so we know that lambda equals Li. All right, so when lambda equals Li, what I'm showing here is here's lambda and here's I. The energy, which is I d lambda, is this area right here. You never did that in calculus. In calculus, you always did the area between a curve and the x-axis, not the curve and the y-axis. All right, it's an ugly thing to do. This energy here is something called the co-energy. And I don't want to talk about it because it's confusing. It is something that you would need to worry about in real machines. But for most machines that we deal with, we can make the assumption that those 2 areas are the same. In other words, we make the assumption that the material is magnetically linear. So lambda equals Li. This is not true if the material can saturate. In other words, remember we talked about this before, L can be a function of the current, right? If the material saturates. We're going to assume that it doesn't, in which case it's always the case that the energy and the co-energy are the same, all right? So what I'm going to do is I'm going to use that result. If you want to understand that more, you can read through my notes, all right? But I'm just going to assume that those 2 integrals evaluate to the same thing. In general, they wouldn't, but I'm going to make the assumption that they do, all right? And so if you go through all of my stuff there, basically determining the expression essentially becomes almost the exact same thing of what I had before. All right. I just want to point out that what I have right now is lambda. So the change in energy is equal to lambda dia plus lambda dif plus torque d theta. Now, you guys are glossing over going, what the heck is he talking about? If you look at what I had before, it was Ia d lambda A plus If d lambda F plus tau d theta R. This integral is hard. This one is easy. All right. And we're going to see that one as we go through. Now, again, I follow my same 3 steps. Okay. So basically, this first step doesn't change anything. All right. I'm changing theta R. Then I'm basically adding in the A current. Then I'm adding in the F current. And I'm done. All right. So here's the process that we use. Step 1 never matters. It's always 0. What I have to do now is to figure out, okay, what happens if I add current into coil A? All right. Well, looking at what I had before, all right, let's just write it here. The change in energy. And I know this looks complicated, but it's really not. All right. So I have lambda A dia plus lambda F dif plus tau theta R. All right. What we're saying in this step is that this guy is equal to 0. Okay. So this guy simply becomes lambda A dia. All right. If there's only current in coil A, this is simply LA dia, and it's just 1/2 LA squared. It's simple. The third step is to do this with IF and IA both acting. So what we do is we say I've got LA IA plus LAF IF. So I have the energy I got in the second step, and now I compute this integral, which is, so I keep the 1/2 LAIA squared, plus I have to do the integral of this guy. So it's LAIA plus LAF IF, and I take the integral of that with respect to IF. All right, this guy stays. If I think about what this integral is going to become, if I'm taking the integral with respect to IF, right, and I got to be careful here. This should be LF, sorry, make sure I'm writing this straight, right? This is LF IF. This is LAF IA, because I'm talking about coil A. All right. So when I take this integral, this guy right here is in terms of IF. So that becomes 1/2 LF IF squared. This guy here is basically a constant with respect to IF. So it becomes simply LAF IA IF. All right. So by the time everything is all said and done, right, what I have is that the total energy in this thing is a fairly simple expression. It's exactly what you would expect it to be. LAIA squared plus 1/2 LF IF squared plus LAF times IA IF, like that. All right. The first two terms you would are things that you would probably expect. The third one there is one that comes in with the co-energy. Now, because of what we've said before, all right, where we sort of derived what is this relationship between the two coils, what I would say is that this guy can be written, I substitute this in to that term, and I get 1/2 LAIA squared plus 1/2 LF IF squared plus M cosine theta R times IAIF, like that. Okay. All right. This is the sort of the important result. All right. The key thing, again, just like we showed before, and again, you can run through this derivation, but essentially the torque or the force is the rate of change of the energy with respect to the thing that can move. In this case, theta R is the thing that can move. So when I look at this expression, right, this was the expression that we had before. Does this term here and this term here, do those depend on position at all? This is my check to see if you're still awake. Do
Only
those
one
depend on
supposed to
position?
would be the degrees, the theta
Yeah.
r.
Yeah, this is the only one here that depends on position. So when I take the derivative of this expression, this term goes away and this term goes away, right? And so I end up just taking the derivative of the M cosine theta R IAIF, like that. All right. So if I take the derivative of that thing, it becomes negative M IAIF times the sine of theta R. Now, if I think about that, if I look at the picture that I've drawn right here, to suggest that that has a negative sign would mean that this would rotate. If I set this up, this guy would rotate like that. Now, I'm actually going to make sure to take you guys in the lab next week to actually see that, because that's exactly what it'll do, is it's going to try to align their two fields. So the F-axis is going to move towards the A-axis, is what the negative sign says. And if when theta R is equal to 0, the torque would be 0 because they would be aligned with each other. Okay, that's what this is saying. All right, so this is ultimately what our result would tell us. All right, is if the torque is maximum when theta R is equal to 90 degrees. In other words, if this guy moved all the way over there and I suddenly applied a current, it would pull it really hard over towards 0. And at theta R equal to 0, it's naturally going to sit and be happy. All right, and the two fields are going to be aligned. Now, in general, all right, is my question of what happens if I have a synchronous machine that has P poles. All right, so what I did here was I showed for a 4-pole machine. And what I wrote out here is, and I don't know why my stuff looks weird there, but I'll make sure in the notes I post to fix whatever lambda B's problem is. But if I look at what's going on with lambda A in this machine, all right, what I see is that for this P-pole machine, all right, theta R, all right, theta R is this angle. It is the physical angle in real space between the A-axis and the F-axis. Electrically, we said that is this angle here is the, so theta electrical, right, is P over 2 times theta R. Okay. So if I look at, having multiple fields, I'll see that that guy actually, or sorry, multiple poles, that guy ends up being different. All right. So if I have this four pole 3-phase machine, my fluxes end up being this kind of complicated looking thing. So what would happen in this particular case, right? So if I wanted to calculate the energy, what I do is I say, all right, so my step 1, you never do anything. This is step 2 here. Right? So step 2, I put in IA, and I only have I see what the energy is if I only had IA in the system. Then I turn on IB, and I see what happens if I have IA and IB. Then I say what happens if I have IA, IB, and IC. And then I see what happens if I have IA, IB, IC, and IF all together. All right. That's how I ultimately do this. So if you go through, I've got the derivation here again of how I would approach this. It basically ends up being one integral with IA, one integral with IB, one integral with IC, and one giant integral with IF. And if I go through that calculation, I end up getting basically this final result. So if I want to calculate what the torque is the derivative of that energy with respect to theta R. This is kind of the important part. If I look at these terms, this one, 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 this one. Do any of the terms that I just marked, do any of those depend on theta?
No.
No, none of them do. So the only ones that do are these three. So when I take the derivative, those three are the ones that ultimately matter. All right, so taking that derivative, if I do that carefully, ends up being negative P over 2 times M times IA, IF times the cosine, or sorry, not cosine, but so the derivative of this guy would be a sine P over 2 theta R. And the derivative of this one and this one are the exact same, except they're shifted by 120 degrees. All right, so there would be two more terms, one from here and one from here. If I carry this all out, I end up getting a complicated expression. And in general, what I do is I put in my 3-phase currents. If I put in my 3-phase currents and I work through all of that, basically what I get is an expression for the torque that depends on the angle of the rotor initially at time t equal to 0, so the beginning of each period, and whatever the power factor angle of the current is. Don't want to get lost in that expression for a second. I think the key thing for you guys to be able to understand how to approach your homework would basically be looking at this result here. What I'm showing here in this result is how I would calculate the torque and the energy if I have a 2-pole machine. What I ask you to do is basically the same thing in problem 3 of the homework, except what you're doing is you're doing it in that particular case with the 4-pole machine, right? So really the only thing it changes is what that flux coupling is, right? So it's basically M cosine P over 2 theta R. All right. We don't need to understand all the gory details of this stuff, but you need to understand at least the high level to be able to understand exactly how to perform the analysis. All right, so I'm going to stop there with my lecture, and I can hang out here for a couple more minutes.